Welcome you again for this course. We are in the module 2 and this is the second lecture in the module 2. The module 2 is the topic of this module 2 is wave propagation in compressible medium. Now, just to give the brief introduction what we have seen in the first lecture of this module, that is introduction to compressible flow. We will say that we bring into parameter, that is compressibility, into account. Then you discussed how wave propagates in a compressible medium, and when it when the smallest wave is generated in the medium, we call this as a sound waves. Now, for the sound waves we derive these one dimensional flow equations. Then we talk something about isentropic flow. Now, moving further, we will continue it from here again, and we will here also will continue with isentropic flows. Also, we will talk about this one dimensional flow equations, but in a different context. Apart from this, the last component of this lecture is the characteristics properties of a compressible fluid. Now, when I said that it is a for an isentropic flow field, we say that a system undergoes a change of state from 1 to 2, and when the process is isentropic. So, the essentially basic feature is that when such a change takes place 1 and 2, we can represent that change to happen in a small volume. We call this as a control volume, as shown in this figure. So, the flow fields before this is condition 1, flow field after this control volume is condition 2, and this process undergoes in isentropic manner. But in other words, in the last lectures we also defined the concept of stagnation properties. That is again a situation where we hypothetically bring the state isentropically also to the condition which is called as stagnation. So, when a state 1 becomes a stagnation state, we define these properties to be P naught 1, that is pressure, T naught 1 temperatures, rho naught 1 that is density, E naught 1 is that is total energy. Now, when you bring this flow to stagnation situation, we say that you are bringing this U 1 to be 0. Now, similarly, since condition 2 is also another arbitrary situations, we can also bring this flow conditions to be also stagnation. So, that situation also we will have U 2 is also equal to 0, P naught 2 will be P 2 will become P naught 2, temperature will be T naught 2, density will be rho naught 2, and then total energy will be E naught 2. Now, these two conditions also needs to be same. So, what it means that any arbitrary flow fields can be brought to a stagnation states, and essentially stagnation states are nothing but the another definition of a given flow field, and we also assign them with certain properties. Now, coming back to these things, when we talked about an and all this case, we say that process undergoes a change of state from 1 to 2, that process is isentropic. But what we are trying to say is that when both these conditions become stagnation and they are essentially same, we call this as P naught, T naught, rho naught. So, this P naught, T naught, rho naught, how we are going to evaluate. So, for this reason, second law of thermodynamics talks about a property called entropy, and in this case the flow is isentropic. So, change in entropy from state 1 to 2 is 0, and the entropy equations has been given through these fundamental principles, where there are two equations essentially. When you know the static properties like pressure, temperature and specific volume, one can calculate the entropy change. So, let us talk about the first equations. When we are talking about gas, we are talking about this calorically perfect gas. When you say calorically perfect gas, we are talking, you are using two important relations, that is Cp is equal to gamma r by gamma minus 1 and Cv is equal to r by gamma minus 1. Now, these two things we are going to put here and we shall be solving these equations. When we are solving these equations, we can write this as ln T2 by T1 is equal to r by Cp ln P2 by P1. Now, when you put this r by Cp from this equation, then this happens to be in this situation, like we can say P2 by P1 will be equal to T2 by T1 to the power gamma by gamma minus 1. Okay. Now, it happens to be the case that if your condition 2 is static and condition 1 is stagnation. So, you can write this as P naught by P will be T naught by T to the power gamma by gamma minus 1. Now, from this similar expression also we can do same way, but here we have to use the relations for Cb is equal to r by gamma minus 1. Now, from these equations we can rewrite, we can also say volume this B 2 by V 1 will be equal to T 2 by T 1 to the power minus 1 by gamma minus 1. Now, here also we will say specific volume is 1 by density. So, this equation can be written in terms of density. So, finally, we are going to say the condition 2 is static and condition 1 is stagnation. So, we say rho naught by rho will be equal to T naught by T to the power 1 by gamma minus 1. So, now we will move further to derive another relations. So, in this relation in the previous relations we talk about pressure, temperature and density. Now, we did not bring into the flow speed into account, and we say that compressible flow is also a function of the flow speed. Now, flow speeds are essentially characterized through this non-dimensional number, that is Mach number. Now, let us see that if any flow field has pressure, temperature and density given as P, rho and T, and this flow has certain Mach number m, then and when it is going or it is moving through in a compressible medium, what will happen to the corresponding stagnation properties P naught, T naught and rho naught. So, this is how we are going to calculate when a flow is isentropically brought to rest and to reach the stagnation state. So, to do that, our the first task to derive these relations, we have to look into this particular expression, that is temperature. So, the temperature is fundamentally related to this energy equation. So, you recall this previous lectures where you talked the total enthalpy as H naught is equal to H plus U square by 2 for a one dimensional flow. Now, these equations can be written as C p times T naught plus C p T plus minus C p T is equal to U square by 2. So, bring C p to the other side. So, you can write T naught will be equal to T plus U square by twice C p. Again you recall C p is equal to gamma r by gamma minus 1. When you put this equation here, this equation turns out to be, and also we will also talk Mach number is equal to u by a, where a is your speed of sound written by square root of gamma r t. So, when you use these equations here, then this turns out to be T naught by T, that means you divide both sides, T will be equal to 1 plus u square by twice into gamma r by gamma minus 1 into T. So, this when you put these relations, one can arrive at the fundamental relation between stagnation temperature and static temperatures as gamma minus 1 by 2 u square by a square, and u square by a square is nothing but m square. So, this means T naught by T is equal to 1 plus gamma minus 1 by 2 into m square. Now, knowing these relations, we can recall the similar relations between pressure and temperature as P naught by P is equal to T naught by T to the power gamma by gamma minus 1. When you substitute these equations, we will land up in this expression. P naught by P will be is equal to 1 plus gamma minus 1 by 2 m square entire over power gamma by gamma minus 1. Another relations of isentropic relation one can bring out as rho naught by rho is equal to P naught by P to the power 1 by gamma. So, you know relations P naught by P from these equations, and when you substitute, we will arrive at this relation rho naught by rho is equal to 1 plus gamma minus 1 by 2 m square entire power 1 by gamma minus 1. So, this is how we derive the relations between stagnation and static properties in terms of Mach number, which is most important, and in fact, this is also called as isentropic relations. So, whatever I have told, it is summarized here, that is what we did is we found the relation between static and stagnation properties for a given flow field. So, here I need to emphasize that the actual flow field need not have to be isentropic, but we can assign the stagnation properties as a hypothetical state for a given arbitrary flow field. Now, we will move to the one dimensional flow equations in a different context. So, in earlier situations we are talking about any arbitrary properties of a given flow field with respect to stagnation flow field, and this is related through isentropic manner. That means, thermodynamic process has to be isentropic. Now, we will see the another situation that when a thermodynamic states moves from 1 to 2 through a control volume in an isentropic process, what will be the one dimensional flow equations. So, essentially the properties which we are talking about, the velocity, pressure, temperature, density and total energy, and in fact, in the downstream side also we have same properties. So, here what we are assuming that we think about this flow field to happen in one dimensional manner, that is we have a constant area duct and entire flow field is one dimensional, and here in our subsequent analysis our work transfer is not important. So, we will say we do not will assume that the flow is changing its states without having any work transfer into the medium, that means there is no work transfer, but still this the control volume can do the energy interaction in terms of Q. Okay. So, with these assumptions we will now move to the one dimensional flow equations. So, here we say that Q is the heat added into the systems. So, obviously, we will be talking about three important equations, that is what we discussed in the last module, continuity equations, momentum equations and energy equations, and all these equations are addressed through the control volume approach. So, we will through integral form of those equations one can write these continuity equations as rho 1 u 1 is equal to rho 2 u 2. And similarly, we can also derive this momentum equations, that is the second part of these equations. I think this analysis is simple, just you have to talk about the nature of the forces here and simplifying the equations. So, the momentum equations says that P 1 plus rho 1 u 1 square is equal to P 2 plus rho 2 u 2 square. And moving further, which is the energy equation, and it is mostly important. So, here we are saying that only the system undergoes the change of state only through work through heat transfer. So, that is what this heat transfer term, that is heat added into the system, is to taken into account, and entire in fact all for all the equations we are saying that area is a constant area. So, that is A, and another parameter of interest is the total energy. Total energy consists of here in this case here there is internal energy U and the kinetic energy u 1 square by 2. So, here we represent this internal energy as u internal, u subscript internal, that is for the state 1 and similarly for state 2, and flow kinetic energy will have u 1 square by 2 and u 2 square by 2, and we are neglecting the changes in the potential energy. So, that term is absent here, and in fact entire equations will have A common, and finally, when you simplify that equations we turn out to reach at this stage where we define this each term of the equation in terms of energy per unit mass. So, when you say energy per unit mass, the first energy, that is q dot by rho 1 u 1 A is nothing but heat added per unit mass, and this is represented in terms of small q, and internal energy and this flow energy or flow work is happens to be the enthalpy, and kinetic energy term remains as it is. So, this is the one of the fundamental equations that is utilized in all subsequent analysis. So, if the summary of these equations, we will have continuity, we will have momentum equations, we will have energy equations. So, these equations are the thermodynamic change of state from 1 to 2. Now, moving further, we will now talk about another segment, that is characteristics properties of the compressible fluids. in all previous situations we discussed about the thermodynamic property, we discussed about fluid mechanics properties, we discussed about the stagnation properties of a given flow. Here we will now bring into another concept which is called as characteristics properties. So, what does this mean? So, in all previous cases when we talk about these properties, we give the thermodynamic definition for the for its change of state. Like in the stagnation case, we say that fluid was brought isentropically to rest. So, in this case what we are trying to say is that in a given state, given arbitrary state of the fluid, now this flow when it changes its state to a situations where, so let me redraw it. So, in a medium, when a medium consisting of large number of streamlines, we take certain fluid elements which has some velocity v, obviously it has some Mach number m. So, this is any arbitrary flow. Now, you define a state which we call as a hypothetical imaginary state. So, we define a state, hypothetical or imaginary state, in which we will say that fluid is brought to a Mach number m which is equal to 1. So, in a given flow field when we which is arbitrary in nature, it has a velocity v or u and the Mach number m, obviously it has associated temperature also. So, in this case when you are bringing it to 1, the thermodynamic definition that we give is that the process has to be adiabatic. Now, when you say Mach number 1, the fluid has to either slow down or we increase the speed. That means, fluid element has to be slowed down so that its Mach number becomes 1, or you increase its speed so that its Mach number becomes 1. Now, when such a state is defined, we say it is a star conditions, that is known as this characteristics condition. Now, when you say characteristics conditions, when you either slow down or increase the speed, obviously temperature is going to change. So, in star conditions, we define another new temperature which is called as T star. So, when I say T star, also we can define the speed of sound at T star, that is A star, and that is what we define the speed of sound A star is equal to square root of gamma r T star. So, if you say the Mach number of this fluid is m, which is u by A in general flow field, and when you are defining this A star again with reference to this imaginary state, so we can define another Mach number which is m star, which is known as characteristics Mach number, and this is defined as the ratio of u by A star. So, this is how the concept of characteristics Mach number is defined. Likewise, whichever is related to these star conditions, we can talk about this, we can define any situations as a characteristic state, but very basic bottom line is, in this case the characteristics state is rest when the fluid is brought to sonic state adiabatically. This is the most important definition to it. Now, in a given flow field, when a given flow field is defined as its velocity u, what is the maximum speed it can attain. So, this is we call as a maximum speed, that is u max. So, a gas can attain a maximum state when it is hypothetically expanded to 0 pressure. So, when it is at a 0 pressure, but the static temperature is also 0, that is represented in terms of Kelvin corresponding to this state. So, what it physically means that its maximum speed of the gas represents the state corresponding to complete transformation of kinetic energy associated with the fluid, that is fluid has its own kinetic energy and it gets transferred completely to the gas molecules. It is associated, the motion of the gas is into the directed kinetic energy. So, that means the complete transformation is of the kinetic energy is associated with the random motion of these gas molecules. So, when it is becomes 0, there is no effectively there is no random motion. So, that means fluid has attained its maximum velocity. So, again we can define this for a given state, we can define that what is the maximum speed it can attain. So, again we can revisit the energy equation of this form, H naught is equal to H plus u square by 2 or T naught is equal to T plus u square by twice Cp. We say Cp is equal to gamma r by gamma minus 1. So, this turns out to be T naught will be equal to T plus gamma minus 1 by twice gamma r into u square. Now, here we say u has to be u max. So, when you say u goes to u max, this can happen when T becomes 0, that is absolute temperature. So, u max becomes twice gamma r T naught divided by gamma minus 1 square root. So, this is how we get this maximum velocity for a given arbitrary velocity of u. Okay. Again we will talk about a characteristic speed. As I mentioned that characteristic speed is nothing but the speed of the gas when it is at this tonic state. Again also we can find out same these expressions using the energy equation. So, you can know that how that energy equation is very vital in all this analysis. So, everywhere you are using these energy equations. Here we will use this energy equation for stagnation temperature, T naught is equal to T plus gamma minus 1 by twice gamma r. So, this derivation was made in one of the previous slides, which is this. So, here what we are assigning is that u becomes u star, okay, or u star also equal to a star, speed of the sound at sonic state. So, that m becomes 1. So, Mach number becomes 1. So, for that case we can rewrite this equation as T naught is equal to T star, that is that arbitrary state becomes a star condition, gamma minus 1 by twice gamma r into u square, u star square. So, you solve for u star. So, u star square becomes u star square will become, if you simplify this, we will have twice gamma r T naught divided by gamma minus 1, this will be for T naught, and same expression we can write twice gamma r T star by gamma minus 1, that will be another for T star. Okay. Now, what we will do? We will now simplify this u star square. So, you bring this particular part, we say gamma r T star is nothing but A star square, that is also u star square. When you bring this expression to the left side and solve for u star, we get we will be now left with this particular term, the first expression of the right hand side, that is twice gamma by gamma plus 1. This gamma plus 1 will change because when you bring this expression here and take u star as common. So, we will left with this particular term, that is r T naught. So, basically we have to say use this expression and bring this expression to the left side and then solve for u star. So, ultimately u star would be so this will be in the square root term, ultimately u star will be twice gamma r T naught divided by gamma plus 1. So, further we can write this gamma r T naught will be A naught. Okay. Now, since u star is also A star, we can also write A star to be twice A naught divided by gamma plus 1 square root. So, there is some mathematical jugglery or simplifications one has to make to arrive at this relation. So, whatever I told, I summarized here. Here we will talk about the speed ratio. So, we define the maximum speed, we define the characteristic speed of sound, we define the stagnation of the speed of the sound. So, what it essentially means, for any given state, that is which is arbitrary, this arbitrary state, for this arbitrary state we can define an imaginary state and this imaginary state is achieved through the adiabatic process and conditions are defined through star. For same arbitrary states we define stagnation state. For these conditions we defined as O, subscript O. So, when we try to make relations between this imaginary state and stagnation state, this is how we define. That is, first one is stagnation speed of sound, maximum speed of sound, characteristic speed of sound. Then you can find this ratio A star by A naught, U max by A naught and U max by A star. Now, here we can see that all these expressions are function of gamma. Now, for air with gamma is equal to 1.4, one can fix this ratio as follows, that is A star by A naught is 0.92, U max by A naught is equal to 2.24 and U max by A star is 2.45. Now, with these basic concepts and the defining these properties, we will now visit the information through graphical manner. So, what does this mean? we will define a term called as adiabatic ellipse, because most of us known as what is a ellipse, which is a very common mathematical term. And here we will define an ellipse which is adiabatic ellipse. So, in a compressible flow field, this adiabatic ellipse is a graphical representation of speed of sound as a function of speed of gases in a steady flow medium. So, as you know, Mach number is equal to u by a. So, it is essentially the relative speed between u and a defines the Mach number. Mach number becomes high when speed of the gas is high for a given conditions. So, it has also another implications, that because u happens to be related to the kinetic energy of the gas, and a is related to random motion in terms of the disturbance. And based on this particular concept, we can now derive these equations for adiabatic ellipse, that as u square by u max square plus a square by a naught square is equal to 1. So, as I mentioned, we know what is u max, that means how a gas can attain maximum speed, and we also know what is the stagnation speed of sound at the stagnation conditions for a given gas. So, this turns out to be the equation of an ellipse in terms of mathematics. Now, let us derive how we get these equations. So, to start these equations, we again revisit the same energy equations, that is Cp T naught is equal to Cp T plus u square by 2. Now, we can say in this, since we are using a mathematical term, we say this happens to be constant. So, assign a term which is a constant C. So, what you do now, we can write these equations as u square by 2 plus Cp we say gamma r by gamma minus 1 into T is equal to some constant, let us say C1. So, gamma r T is nothing but a square. So, this will implies u square plus twice by gamma minus 1 into a square is equal to C1. So, take this, let us find what is this constant C1. So, here we will try to bring how we can get u max here. So, to get u max, we have to say that when u goes to u max, at what conditions? So, you rewrite this equation in this manner, that is u max square plus twice by gamma minus 1 a square So, what we will do now this. So, we say u t goes to 0, u goes to u max. So, we can write u square as plus twice by gamma minus 1 into a square as u max square, because this C1 becomes u max square, where t is equal to 0 and a goes to 0. So, C1 becomes u max square. So, when you say this, this is how. Then we bring what is this u max square here. So, what you do here, to use this equation, we can say u square by u max square plus twice by gamma minus 1 into a square by u max square is equal to 1. Okay. So, from this u max square you bring these relations from the earlier one. So, we put u max square from this, then we rewrite equations as u square by u max square plus twice by gamma minus 1, and here it will be reverse, gamma minus 1 by 2 a square by a naught square is equal to 1. So, these terms will get cancelled. Ultimately, this leads to this expression u square by u max square plus a square by a naught square is equal to 1. So, these equations is a term, this is how we derive this equations for adiabatic ellipse based on the starting with energy equations. Okay. So, now let me see that when you take this adiabatic ellipse equation, how you represent it graphically. So, this is the equation of the ellipse. So, we are plotting this graphically, where x axis represent u, y axis represent a. We have a gas can attain maximum velocity, that is u max, which is given by the abscissa of this ellipse, or that is half of the major axis, and the stagnation speed of sound a 0, which is defined by this point, which is the half of the minor axis of the ellipse. So, at every point on this ellipse, we can define about the relative importance between u and a. So, when your Mach number is equal to 1, which is u by a, that means essentially u and a are same. So, we can drop a slope from this point. This point can be located, that is from origin we can draw a line 45 degree, and wherever it touches the ellipse, at that point we will have Mach number is equal to 1, because this u and a will be same, that is slope remains same. So, this is how the physical significance of this adiabatic ellipse. So, what it means, that change in the slope from point to point indicates the change in the Mach number through relative change in the speed of sound and velocity of the gas in the medium. Okay. So, here we will now talk about something more, what is called as a sensitive analysis. What we essentially trying to say, that how we can relate this Mach number with the slope of this curve or ellipse. So, for that what we can find out from this equation as, so we want to find out this particular expression, that is dA by du. So, to find these equations, we start this equation, that is basic equations, and from these basic equations you try to find out this dA by du. So, how do you do it? So, we separate this equation as a square by a 0 square is equal to 1 minus u square by u max square. Then what you do? Simplify. A square is equal to a 0 square minus 1 by u max square into a 0 square. 1 by u max square into a 0 square. Then you find differentiate. That is 2a dA by du will be equal to minus a 0 square, here there is a missing term, u square, a 0 square by u max square into u square, you differentiate twice u du, sorry, twice u du, we have taken it here. Okay. So, now you try to find out a 0 square by u max square from this equation, substitute here. Then when you substitute, then we say dA by du dA by du will be minus gamma minus 1 by 2 into m. M you get because you get a comes to the left hand side, a goes to right hand side, we get this Mach number, and or m is equal to, we get this reverse minus 2 by gamma minus 1 into dA by du. So, through the sensitive analysis we get the Mach number or slope, Mach number which is related the slope of this slope of the slope at any point on the ellipse. So, now let us revisit what does this mean. So, what we have drawn here, to study the effect of sensitivity of Mach number with respect to slope, we have taken only the 1/4 portion of the ellipse, that is the first quadrant. So, just to see this relative importance, we are now trying to define different flow regimes. So, just looking at this curve, one can make out that when we are moving towards, when or u tends to 0, when you move towards left, that means we are going closer, when we are going closer to 0, although we have speed of sound as maximum as a naught, but we are in the situation that the flow field becomes, the speed has no effect in the medium. So, for that reasons we say that we are moving towards incompressible medium when u decreases, but as and when u increases, that means when we are going towards right hand side, then u keeps on increasing. So, relative importance of u increases more and more as we move towards this. Now, coming back to this figure, here we have defined essentially 5 regimes of flow. So, first thing is that in the first regime, when you say the flow to be incompressible, that is defined in the first, defined as I. So, where the flow is incompressible, that means we are in the domain of incompressible region, and you choose that point in such a way that that particular point your Mach number becomes 0.3. So, that means as long as we are in this domain, the flow is incompressible in nature. That means the flow is incompressible flow, and the role of Mach number does not come into picture. Now, as we move towards the region 2, which is this, the Mach number keeps on increases. So, till Mach number is equal to 1, which is drawn at 45 degree, which is shown through a line drawn 45 degree, drawn from the origin to that point where Mach number is 1, the flow is defined to be subsonic, that is second category. So, as and when keep on progressively increasing, so we are moving towards The third region which is flow is happens to be supersonic. And in some field some dominance region like flow is neither flow is in the vicinity of subsonic, but trying to going to supersonic region, or in other words flow is initially supersonic and tried to goes to subsonic regions. So, those regimes are defined in certain Mach number range, that is 0.8 to 1.2. So, that is denoted by domain IV, that is fourth region, that is transonic flow. And the last part which is flow happens to be hypersonic. So, we are in the last part, that is V, fifth region, this is flow is happens to be hypersonic. So, in this domain we say that we are moving flow towards the hypersonic regime. So, the last part of these things whatever I have explained, which we get we talk as inferences from adiabatic ellipse, that is change in the slope from point to point indicates the change in the Mach number relative to change in the speed of sound and velocity of the gases. So, it gives the direct comparison of relative magnitude of thermal and kinetic energy in the steady flow compressible medium. So, what it shows from the adiabatic ellipse, that at low Mach numbers flows, the changes in the property parameter are mainly associated with the change in the velocity of the gases, and the at high Mach number flows, the changes in the property parameter are mainly associated with the change in the speed of sound. And in the limiting case, when Mach number is in the range of 0.3 or less, the flow is treated to be incompressible. These are the important inferences that we get from this adiabatic ellipse. So, with this I conclude my talk. Thank you for your attention.